contests. Here we go. Game of life. Oh, and one more thing, just to later allow you to easily find the problem. I will not spend a lot of time on easy problems, so let's go. Problem A. We need to simulate the process, and there are m steps, and m is a lot, but here's the observation that I basically guessed. There is, after first n steps, there is a cycle of size 2. That was my observation, at least my assumption, I guess, where you get some new cells that are infected, right, or alive, but eventually this will stop spreading. Actually, can it happen that... I don't remember. Maybe just it stops, right? I think I solved the harder problem. Is this true? Please just somebody tell me in the chat if it's enough to simulate minimum of n and m steps. It's true? Okay, cool. Then I did something more complicated with a cycle of size twice n. And this is quite obvious, just because 1 will spread through an interval of zeros, and eventually this interval of zeros will be done. An alternative would be to look at the size of interval of zeros. Then we can, in constant time, say what happens with that. My opinion about the round? I guess it was fine. I don't know. D defeated me. Now I know a solution for D. Right, second problem, B. We can add two numbers or subtract, and every number we need to change into its negative version, and we can use at most some number of operations. I can just show you how I experimented. So I just, I wondered if we start with two numbers, 5 and 7, and it's a hint that n is even, right here. It's for sure a hint, and it means that we should do something for pairs, because most likely we should do something for pairs. If the first two numbers, if for them we can make them negative, both, in few operations, then maybe we will do that for every pair. Then what did I do? Starting from 5, 7, I experimented a little bit. We can add 7 to 5, that's 12. Then we can do some subtraction, like this, and already I see -5, but this should be -7, and like that I continued. This is how I experimented. I tried one thing, I tried the other, and this one worked, where now when I have 12 -5 after two operations, I subtract once more, so I have -17, and thanks to that, in one operation I can fix the left number. So the key was to get this in 4 steps. The number of steps doesn't really matter that much. But I already got here negative version of initial 5. And then with few steps I can change this by 5, and by 5 I will get -7. So really spend a few minutes on a piece of paper and eventually we'll get it. From 5, 7 I got -5, -7. I can do this for every pair. I needed 6 operations. 6 operations per two numbers, so per every pair, then 6 times 500 operations in total. That's 3000, because there is 500 pairs. And I think we can continue. Next problem, C. What did we do in C? The statement maybe wasn't trivial to understand. In particular, I didn't understand that those are dots. I for a moment thought maybe it's multiplication. I was a little bit confused, but well, those are dots, and the drawing helped me. And always here, when we start from, let's say 1, then we have 1.1, maybe 1.2, 1.3. what we are allowed to do is we can continue with this 3 can change to 4, or we can continue with this 1 can change to 2. So I represented this as some kind of stack, or just vector, where I know now that the next number can be 2 or 4, or 1, if 1 means just adding a new element. Right? From this, if now next element is 4, this is what I want to get, then I know that, well, this is at the end of some string, in this case 1.3, and I can change this 3 into 4. In this case, there is a unique thing I can do. I need to change 3 into 4. Let's say that the next element is 2. Then I need to change 1 to 2. The new stack will be this, and it will represent actually something like this so far. So this is what you would have so far in the output, while this is our stack. What if now the next element is 3? Well, it means you need to change this 2 into 3. Always, if you want number x, you need to look for x minus 1 in your stack. So now we have this. And the tricky question is, what if now the next element is 4? What do we do? I have a choice between changing one of them into 4. My operations so far correspond to this output. And what do we do with that? I have a choice to put here 4 or to put here 1.4. And I just need to say which version is better. I messed up, didn't I? Yeah. Now, when I modified this element, this one got destroyed. Because if you want to now from 1 change it to 2, you lose the ability to use that. So sorry, and thank you, chat. Like this. Okay, but what if we actually have a non-unique choice? So let's say it's like this. Now this list or stack is 1, 1, and now we want 2. That's the non-trivial situation. I have a choice between putting here 2 or putting 1.2. Then here's the thing. This version is better than putting 2. Why is that? Because now our list is 1, 2, and if the next element is 3 or the next element is 2, I can handle that. Next element can be 2 or 3, and I will be fine. But if instead I just did this, now this is my list, I lose the opportunity to use 2 as the next element. Let's consider the input elements to be in order 1, 1, 2, 2. If those are the input elements, and so far you did this, then for 2 you put it like that, you cannot create another 2. You would need to here create 3. But instead, if you did this, then you can get another 2. Like that. So here's the algorithm. Always when you have some kind of A, B, C, D, and now you want to get element x, you're looking for x minus 1 here. Well, first, if x is minus 1, put at the end, which just means to expand the list like that. Otherwise, what do? Look for x minus 1. This is some strange mix of pseudocode and algorithm description. Look for x minus 1 in this sequence, and we need to do it backwards, like in the example explained here above. If d is equal to x minus 1, great, just replace d with x. If not, then pop d, and check if c is x minus 1. For example, if c is equal to 4 and x is 5, like maybe, let's say this, and now you need 5, sure, great, we change 4 into 5, and that's it. So greedily, we try to change the last element to the version greater by 1. If that last element doesn't match, then we pop it. We continue doing so. If they told us to say impossible, if this input sequence was impossible, then what we would need to do is just whenever we have already an empty list and we try to pop it further because we want, for example, to get element 5, that's impossible. Done. Questions? I think this should be best kept as a vector, by the way. So for me this would be a vector 1, 2, and always I'm looking at vector.back, and sometimes I pop backing. How to prove backwards is always good. In short, because then we have only more possibilities. If you change element that is more to the right, you have more possibilities of what will happen in the next step, and thus also more possibilities of what will happen in further steps. But that's not a formal proof. E was recursive. What was E? No, E isn't recursive. Right, C done. Also, please show me my results so far. Still in the queue, but should be judged. No, still a lot of time. All right, now problem D. Worst contest in history? Why? Why was it that bad? Love-hate. This is a problem I didn't solve during a contest, but I know how to solve it now. Somebody told me one sentence and that was enough. Whenever you see something like this, that's a general rule. Whenever you see at least n divided by 3 or at least n divided by 5, something like that, think randomization. I think 90% of cases this rule will work. If you know that the answer or the set of elements we need to choose is very big, we can, and this is what we will do in this problem, let's say 20 or 30 times choose a random element and assume that this is part of the set of those friends. There is probability half that you didn't get it right. If there is that optimal solution, let's say, it uses some set of friends. Then with probability only half, you didn't get any of those friends. If you repeat 30 times, you have probability half at power 30 that you didn't get it. So for sure, this is the first step. And then what do we do with that? We assume that this guy is one of those friends, and we look at his string. Let's say this is his string. Then we know that if he should be one of those chosen friends, then answer must be subset of those ones. And there are, of course, 2 to 15 subsets, possible subsets. If we consider all of them, and we repeat that 30 times, great. So, and here's the solution I got during the contest that I came up with, but that's too slow. Repeat 30 times. Let's say I is random person. Iterate subsets of his ones. Ones in mask representing this, so maybe subset in S of I. S of I is ith string from the input. Well, there are 2 to 15th of them. And count friends with that subset. 30 times get random person, iterate over all subsets of his set of ones, and then go through all n friends and count how many of them also have this subset on. The complexity, sadly, is of 30 times n 2 at 15 times count friends, that's n. This is way too much. We need to speed this up. When you look at particular friend and you check if he has that subset, you can do that with bitwise operations, so that's very fast. Also, 15 should work well, maybe even 10 if you're lucky, or if you're not unlucky. You can do this fewer times, but this is anyway too slow. And when we deal with subsets of particular set of bits, then the way to go, and this is what I didn't come up with during a contest, is sum over subset, also called SOS. If you Google Codeforces SOS tutorial, you will find something. It's here. I don't know if this is the best one, but there are plenty, and we will use that. How we will do that? I think that my goal is to get complexity down to this, because now instead of this brute force I will do this. Iterate over subsets. No. For every person among all the people, count of his subset plus, then run SOS, and then iterate over subsets of SI and check if count is at least n over 2. Round it up, of course. That's the solution. What does this his subset mean? This is actually S of I intersected with S of j. And then we do sum over subset over this. So what does it mean? Let's say that our SI, person who we assume he's in the group of friends that should be chosen, is this. Let's say then that S of j has those bits on. And this. Then, because I know, at least I assume now, that the answer, by answer I mean group of bits chosen, is subset of this, I'm not interested in those. Right? So intersection is 0, 0, 0, 0, 1, 0, 1, 1. This is intersection, and we do count of this plus plus. Because this friend, J, if he also should be in the group of friends who have that common topic, common bits, from him we only care about this subset. And what sum over subset does, it is able to automatically say that we add +1 to all subsets of this. So SOS handles the fact that also I want to say, well, if this group of bits is chosen, that's fine. Friend number J knows those bits. If we want to choose this, yeah, that's also fine. If we want to choose just that, also fine, and so on. SOS handles that quickly. We don't need to iterate over that. And then indeed, instead of having here 2 at 15 times 100,000 or 200,000, we have 2 at 15 plus n, plus 200,000. Because we used SOS, sum over subset. Do I consider partnering with Twitch? Not really. Hard problem for D? Maybe. Well, not maybe. It for sure was hard. And we can see that by looking at the number of submits. Like we had here a lot of submissions, and then it dropped by a lot. And a lot of people skipped, and instead of D, they solved E. I was one of such people. So yes, this problem was harder than the organizers expected, I think. Did I upload contest stream? Not yet. It will be uploaded after this stream. My contest screencast will be uploaded later. Moving on. Now E. My first idea was incorrect, and I thought that maybe first the statement. There are n slots for something, those are lights, they are off, and in random order we turn some on. Maybe this is now on. Let's say this is marked by uppercase X, or maybe this guy, and so on. We always turn on random light that is still off. And we wonder what's the expected value of time when, for the first time, two lights within distance at most k are on, because this is where this is when the process is finished, and we need to find this. Now, my incorrect idea, at least I don't see how to continue with that, was that after the first x, which is on random position, we can iterate over n possibilities. Let's say that k is 4. Then we have some forbidden positions, those where we don't want any lights. And I thought that maybe we should go recursively to this allowed part and that allowed part to say, well, you can continue there as long as you want, and those two are quite independent, but there are a lot of issues there. Actually, they are not independent because you choose lights from the set of all available slots. That's one thing. And the other is we have those forbidden positions. So the number of forbidden positions matters a lot. And yep, that's not a way to go. So that was a wrong idea. But now, a good idea, something that actually worked, is to use combinatorics. Instead of this, if you have time, let's compute some kind of probability. And if you want, you can focus on something like this. Probability of, let's say, 5 lights on. Why not? Or maybe 7 lights on. I don't want to draw that much. Let's start with 2. The probability that we still are not dead, that after 2 lights we continue the process. So what's this probability? Well, the first light will be on somewhere, and it creates some forbidden positions. If you iterate over position of this first light, then you know which positions exactly are forbidden, in this case that and this. And then you can say what's the probability here. But this doesn't translate well to a bigger number of lights. And this is why instead I want to use combinatorics. What's the number of ways to choose here a pair of positions so that distances would be proper? Let's say that there is position A on the left and B on the right. In this order, A on the left from B. I can fix the order. If the order is different, then it's symmetrical, let's say. Then after A is chosen, I know that there are only 3 forbidden positions for B. And then B will be chosen somewhere on the right, and it cannot be here, more or less that. Well, still, the number of positions of B, the exact position of B affects where B can be placed. But let's think about it differently. What about this? Whenever we put, whatever is the number of lights, and actually whatever is the order, let's say that the light comes with 3 forbidden cells on the right. Well, 3 should actually in general be k. Or k minus 1, something like that. My f passed? Oh, great. Cool. By the way, I will be barely outside of LGM, I think. What's my time? Still this. I had like 90% of time limit. Tourist 1, I'm not surprised. He usually wins. Okay. Choosing a light comes with k forbidden cells on the right, no matter what's the number of lights. And you can argue that the rightmost lamp doesn't have that, or the rightmost light. I'm not sure if I can explain this thing very well, but this is standard. You should know it. If one light, it actually takes 3 extra cells, then what about this? You have n possibilities to choose the first light, then n minus 4 to choose the next one, n minus 8 to choose the next one, and so on. Something like that, maybe. That's one idea to move forward. And another in general is that we choose from that many elements, let's say that we choose m lights. From that many positions, we choose m. And this is actually very important. This is number of ways to get m lights on and still be alive. C stands for binomial coefficients. So it's this, choose m. What is this? And something similar you use, for example, to say what's the number of binary strings with k ones where no two ones touch. You use the same thing. What is that? Well, we have this limited number of slots. Let's think about an example where k is 4 and m is 2. We just choose 2 positions out of, say, 10. Okay? Normally, from that many positions, you would choose to m equal to 2 lights, but we want them to be far away. So instead, for some reason, I subtract this number, which is here 3. 3 times 1, that's 3. So out of only 7 positions, I choose some 2, any 2 of them. Maybe this one and this one. I don't care if they are close to each other. And then I say this. Every light other than the rightmost, it comes with 3 extra cells. So if in a sequence of 7 positions, I said that here there is one light and here there is another, then for every light other than the rightmost, I append 3 forbidden cells. And that's it. Every here choice of 2 cells out of 7 is equivalent to some good choice of 2 cells out of 10, where they cannot be too close to each other. Those 3 forbidden cells that grow out of every light, they push everything to the right. So even if I chose here A next to B, like this, in 7 cells A and B are neighboring, but then I say from A, those 3 forbidden cells grow to the right. They push everything else. I don't need that after B, because I don't need to guarantee that after rightmost light there is nothing very, very close, because this is rightmost. And yeah, here out of n positions, the number of ways to choose 2 lights, so that there wouldn't be within this distance from one another, well, at least that the distance can be exactly k, but it cannot be closer, is 7, choose 2. And another example, if let's say you wanted to choose 4 numbers, 4 lights here, then the formula will say 10 minus 3 times 3, choose what? Choose 4, that's impossible, right? Let's go with that. This is 4, choose 3. There are only 4 possibilities, it seems. And here, out of 4 slots, I choose 3 of them. Let's say that they are like this. And what does it represent? It represents A with those 3 forbidden cells and B with those 3 forbidden cells. By forbidden, I mean empty cells, and those need to be empty because otherwise you would be close too close to A. So yeah, that's it. And you can examine what happens if instead out of those 4 slots you choose, let's say here, A, B, C. Well, then you have from A there are 3 empty growing to the right, from B there are 3 empty growing to the right. Always it's guaranteed that there will be 3 empty after every light other than the rightmost one. Now, that was how we can get the number of ways to get M lights on and still be alive. And another trick is that this is enough to compute expected value. If I tell you that, if we divide this now by the number of ways to choose m positions at all, then this is probability of being still alive after m lights. And that's the key. You can assume that if something forbidden happens, let's say that process still continues. We don't want to count that time, but the process continues forever. And now, if I tell you that there is probability 100% of being alive after first step, then probability 30% of being alive after second step, and then 0% of being alive later, then what's the EV? Where there is, from those probabilities, it's easy to compute EV. One way is this. There is 30% that we will be alive for 3 steps in total, because after second step, then you make third step, but that still counts to time. Plus the remaining 70% is that you are alive after first step, and then you make second step and you die. This is something. 0.9 plus 1.4, 2.3. That's the answer. Alternative way of looking at this is, and that's easier, is to just sum up the probabilities. So add 100% and 30%, because there is 100% that you will make, maybe this. First, for sure you will make the very first step, always, no matter what values I put here, now even if this was 50. First step, we always do. Then with this probability, we make the second step. So there's this probability that we make step number 2, and that adds +1 to the answer. And there is 30% that we add another step, another 1 to the answer. So this explains how the answer is 1, because we always make the steps, the first step, and then sum of probabilities that we get, where probabilities are computed like that for every m. M is the current step. Maybe it will not hurt us to spend 1 more minute here. Let's say that I don't know what else I can say here. Maybe this was a bad example because it was with 100%. There is probability 0.4 of being alive after first step, so 40%, and then 0 of being alive later. Then what's the answer? 1 plus this, plus that, plus that. And the reason is that always we make the first step, and for example, this is the probability that we will actually make the third step. So this value, it actually hides probability multiplied by how much we add to the answer with this probability. So here the answer is 1.8. Predictor gives me exactly 3000. That's interesting. Hi, Tim William. I would do much better if I didn't spend time trying to solve D. If I knew that I cannot solve D, I would immediately jump to F, then it would be better. I wasted a lot of time just thinking about D. -10. That's funny. So what will I get exactly 3000? Actually, I think it would be better to be at 2999, because then you're motivated to participate once more. My graph shows that I'm not afraid of losing rating after getting 3000. I participate anyway. how we will take of P over Q. Yeah, like if you're unsure about this part of the problem, this thing, then you can watch my video of computations modulo P. So you can watch this, or division under mod by second thread, and plenty of articles too, if you prefer to read. So you just choose among the numbers of positions in a way that is possible to place k-1 forbidden positions between adjacent pairs. I wouldn't phrase it like that, but maybe you're right. I guess so, yeah. K-1 forbidden between every adjacent pairs of chosen elements. That's right. Finally, problem F. In F, as you saw, maybe, I barely got accepted. I will aim at complexity this to add 40 times m times another m. And while I was solving the problem, I thought that I will get this complexity, which would be fine. This is around 160 million. And very late I saw that I need another for loop inside. So while most of my code satisfies this, at one point I have that with low constant factor. So while maybe this has a significant constant factor, I mean significantly still, like few operations, not 100. But this is a single for loop, and actually this is divided by 4, maybe by 2. So yeah, this is my solution. I got like 1.8 something seconds out of 2 seconds. Let's say this. So it's not that I easily got accepted. And I was careful to make my solution quite fast. To make the implementation quite fast. All right, the problem is that there are n towers and m quests. M is 100, n is 14, and always when we see 14 we think about 2 at n complexity. Maybe we will have masks over that. We have that, and what we can do, we can travel between those, every quest each with desired time, and we need to be exactly at that time, at point of that quest. Every tower and every quest, they have positions, just coordinates. We can move between 2 points. You use Manhattan distance, but that I didn't use that. That could be any kind of metric. And you need to get as many quests done as possible. You just need to say what's that maximum number of quests done. And once you activate tower, you can teleport to the tower from every possible point on the map. So always you can jump to once visited tower. I will repeat again. Always you can jump to an already visited tower. Right. Whenever, well, this is a game, some kind of process when you keep making moves. And at every moment, what's important is your position, your visited towers, and score so far, how many quests you did, and the current time. So 4 values. In particular, position can be from 1 to million every coordinate, so if you use that as dimensions of dynamic programming, that's very bad. You don't want that. Okay, but what about this? You can directly jump between towers and quests. You can just say that from quest you move to another quest or to tower. So actually position, this is just, there are only 114 n plus m possibilities. So not that bad. The visited towers, this is of course a mask, so 2 at nth power. This is 2 at nth power. The current time, that's tricky. This can be up to 1 billion, so let's leave this aside. And the score, this is from 0 to m. This is their m possibilities. This times that times mask is maybe doable. Time can be huge, so most likely we will move it outside, and we will have int dp of position, current position, mask, and score, where this int, it denotes the time. Is this discussed? Yes, I went in order. You can rewind. In particular, you can go to YouTube and you can rewind the stream. Yes, I will upload the screencast. This is the time. Of course, we minimize the time. You might argue that not only score is important, but which exactly quests we did. But that's not important. I don't care about mask of done quests, of finished quests, because the current time, it tells me which quests are already in the past and which are still available. If the current time is 100, among quests that happened until time 100, I don't care which exactly I did. I just care how many of them I solved, how many of them I really were there at proper time. So this is fine. All right, this was my first idea, that we will do this. Doesn't fit in time. It doesn't fit in space. Space complexity of m squared. This is m plus n, but m is bigger. As a reminder, position is either tower coordinates or quest coordinates. So n plus n possibilities. There are that many possibilities for position and score, multiplied by 2 at nth power. And if I have that, what's this? 2 at power 14 times 100 squared. Let's divide that by 1 million. This is 163 times 10 to 6th power. If we use ints, that's this times 4. What's this times 4? 655 megabytes. And maybe you can make this work just by cutting constant by 2 by 2. But better way is to just notice that score always increases by 0 or by 1. So we can make this the first dimension and we can iterate over that. Like only keeping the last 2 rows, only keeping 2 last values of this. So we can improve this to only be m times 2 to nth power, and space complexity is then fine. But time complexity is terrible. For every such state, most likely I will iterate over the next move to make, and that will make it very slow. Like from every quest, if you also consider going to every other quest, that's bad. We don't want that. So my next observation was that it doesn't matter in which tower you are, because if you are in a tower, then always you can jump to any tower out of those visited towers. This mask is mask of visited towers, and always from anywhere on the map you can jump to one of those towers. So maybe whenever we are in a tower, then the current position doesn't matter. So it at least makes the number of possible positions m plus 1, not m plus n, because it doesn't matter in which tower we are. That's something. But to make it easier to think about it, I split dp into 2 dps, 2 arrays. One is when I can be in tower, when I can be in quest, when in tower, let's say, where I only have mask and score. Doesn't matter in which tower I am, because I can jump between them, and from anywhere I can jump to a tower. This is very nice space complexity, and time should also be fine if this is 2 at nth power times 100, then I can even iterate over the next quest or the next tower, and it's fine. I'm fine with complexity. Did I write it up? This time complexity is fine. So if the number of here states is this, states, then O of n plus n transitions. Time complexity is then number of states times time per state. Cool, that's great. But not the only. This is not the only thing I need. The other thing I need is what's the earliest I can be in quest, and that's mask of visited towers, the current score, and which quest I'm looking at. But then what is this int? This int was the time, smallest possible time. What is the earliest I can be here? But wait a moment, quest has predetermined time. It doesn't matter when exactly. So this you can change to Boolean value. And then you can improve it in various ways. Most of the contest I thought that we should do this. Max score, because now one of those dimensions I can move outside, as long as it's okay to minimize or maximize this dimension. I did this, where now int this thing says what's the max score to be in this quest. Right now. By right now I mean at time given for this quest. I will have this array, two-dimensional array, and either I have this Boolean one, or I have this int where I maximize this value. And for half an hour I was thinking about this solution and then coding it with those two arrays, and eventually I found an issue with that, and I decided that it's actually better to switch to this version. You will later see why Boolean array was convenient for me, and how I cheated you with my time complexity. So, well, even though this looks promising, let's move it, let's hide it here. I will not use it. I actually use this. And space complexity is fine because we have Boolean values, and that cuts the space complexity by 8, or sorry, by 4 or by 32 if you use vectors or use bit sets. Just in case you care about space. All right, what do we do here with those two? Well, we will most likely iterate over the current mask, the current score, and maybe even the current quest. But here I need to consider multiple transitions. From tower to quest, from quest to quest, from quest to tower, and from tower to tower is unnecessary. I know that, no, actually it is necessary. This says that from existing tower, where I am right now, I jump to new tower. Also this thing, from quest to tower, either it means that I move to the nearest already activated tower. Oh, no, sorry, that's stupid. I can jump directly. Okay, so both those are not activated tower. And also, from anything, we can, for free, jump to activated tower. This is cost 0. Now, let's say this. From tower to quest. It means that I move from this, so I have some current time, and then that's quite easy to handle. If the current time plus the distance to the quest doesn't exceed when this quest wants to be done, then we say possible. Okay, and for that I iterate over quest first. Like this. This says when I can be at one of the already activated towers. This is the set of activated towers. This is the current score. If this plus distance from one of those towers to the quest, and this is something I pre-computed. This is distance from this mask to the quest. This is pre-computed, and so I could use it in constant time. And this basically says what's the shortest distance, so it finds the closest tower out of those activated towers to this quest. This is when I can be at that quest. If that doesn't exceed the time when I should do this quest, then this is possible. So I say, this is not non-quest, this should just say possible quest. Or just is possible, let's say. Then is possible of mask score plus 1 because I did one more quest, and of this quest is true. Easy enough, and the complexity is fine. That's 2 at nth power times m times m. This is one of the transitions, and we have multiple of them. For quest, what do we do for quest? Well, for quest, and let's actually number them. This is first, this is second. Any questions? I'm not seeing any. Okay, from quest to quest. And what do we do with that? Well, you can do this, iterate over quest, if is possible of being with this visited mask of visited towers, with that current score, and being at that quest. If this is possible, then we can iterate over next quest. And we can move. Like, if time allows, then is possible next quest is true. This is too slow. 2 at nth power times m times m times m. If you for every quest iterate over next quest to do. So what we do, we speed this up with bit sets. Because this time allows, actually it's independent from visited towers. If I want from quest to jump to some tower, then to go to this quest, I will do it in 2 steps. I will first go from quest to activated tower, and then from tower to quest. But I don't, here I directly go from quest to quest. So, is possible for this mask and score plus 1 with bit sets, or this with, I called it jumps from quest. And this, because for every quest we already know when we will be there, if we are indeed there. So I can pre-compute for every quest what are future quests that I can handle from this one. This is a bit set of size 100. So this is operation on bit sets of size 100. I assume that it's constant time. Actually, it's 100 divided by 32. But, well, yeah, now it's done. And this is partially why I decided to actually still use Boolean values. This is a bit, this should be bit set, instead of this int. I couldn't do this trick if I used an int array where I maximize the score. And I first thought that this is still better because the number of states is smaller, but nope, I needed to do something multiple times. Yeah, for every quest from tower to not activated tower, that's also easy. I will not code this fully, but iterate over next tower. No, won't do that. This is anyway slower because you iterate over 100 elements, not over 14. Right, what else? From anything to activated tower. We don't consider really from tower to activated tower because we automatically know that this is possible, thanks to this pre-computation, that we know we are in one of towers. What we should consider really is moving from quest to activated tower. So those two are left. I will later get back to if you want. I now will want to focus on F. But if you're asking about different versions of a problem, then I don't know. You can ask in Codeforces. All right, one of those two should be easy, I think. Yeah, from quest to activated tower. This can be done there as well. Because when moving to activated tower, wait, I did something stupid. From moving from quest to quest. Oh, here I moved from quest to quest. I also want to move from quest to not activated tower. Not to activated tower. How do I do that? Well, I say that the time at quest plus the pre-computed distance, yeah, this is when I can be at one of the towers. So what, when in tower, score is minimize minimum of itself, comma this. That easy. And actually, because we update this value, and here we want to use it, the order should be different. So the order should be like that, because this is where we can actually update this. Yes, I will upload the screencast. And the last thing we didn't do is this one, and I didn't know how to handle that faster, so like those. This one part, it's not complicated, but for this I had sadly slowed this. For every quest, for every tower, I consider moving from this quest to this tower. This is in constant time, just like those previous things, but I have, because of that, to add nth power times m times m times n. And this is, if you see how to speed this up, do tell me. This was fortunately fast enough, because this was just like 1 or 2 operations. And actually it's divided by 2, or maybe even can be explained why it's divided by 4, because the quest cannot be smaller than score if quests are sorted by time. Here you have something like this: if is possible of mask score quest, and already this will not happen from time to time. You know, if questions are sorted by time and current score is already 15, then the quest is at least 15, because, or maybe 14, because, well, you got score 15 already in some quests. So assuming they are sorted by time, which I did at the beginning of my implementation, then this is true. So already it cuts half of states. And also next power, here we iterate only over bits that are off in this mask, because we want this to be new tower. This, depending on the implementation, it can get another divided by 2, and then this n over 4 basically becomes constant. N was anyway only 14. So that's it. Maybe this can be done fast, I don't know. Questions? I recommend during the contest, if you're stuck thinking about a correct solution, but you know it's DP, it helps to write down even some pseudocode to list steps, because then you know what you need to do, and by looking at for loops you see what's going on and what's the complexity. It helps. Here's an idea for the future: project with real-life implementation of a data structure. Many people use that already in things like databases. The best possible tools are being used right now. It's very rare that something can be improved. If they can, then well, that's a good paying job. I can go work for a company and then after multiple months maybe I will be able to improve something with data structures. This format is nice. I will keep that in mind, Rock Robot. That being said, is this that different from C++? If I wrote here every line in C++, it would be the same. This is easy to understand because it's dynamic programming with very easy transitions. Right, maybe writings are done. Not yet. What else we can look at? Whether editorial is posted. Yes, it is. They have 2DP2. So they went with this thing I said I discarded because I didn't see how to handle it. Right? Maximum number of quests can complete if this is visited set of towers. Last completed quest is this. Yeah, this is exactly what I wrote here. And I guess combined with that. Yep. And then they describe all the transitions. And they have this. I implemented this and then I saw an issue. Just because for me an issue was the following. Max score kept changing. If I see, for example, that max score of this mask of quest number 2, let's say this is, or quest number 5, let's say that this is equal to 3. This means that it's possible for me to visit this mask of towers, to be right now at this quest, and so far I visited 3 quests. But then I make some transitions and I didn't know how to get rid of this case where I transition from this to say maybe from this quest we move to another quest or to some tower, and then something else updates this max score to be better, 4 or 5 and so on. And it seemed that a lot of times it will happen that I make transition from this, even though it's not optimal, because in the future it will actually be updated. I didn't know how to iterate in proper order. Or I didn't know if this is optimal or some other state will actually try to improve this, maybe to say that score of 4 or 5 is possible for this. Exactly 3000 according to predictor. Yes, I'm aware, and this is why I will often refresh. Thanks for content I post. You're welcome. This looks like Python. It does, but that's the simplest possible pseudocode for a for loop. I don't know how to handle this. Do they say something about the order? I got the correct idea, I didn't know some detail, and this is why I went a slower way, where one single part was worse. And I believe that this is possible. Later I will actually read the editorial, or maybe read code, if they include here some code by organizers. So what? People didn't like the contest? Now I'm done talking about problems. And actually I'm interested in what people thought about the problems. Oh, needed priority queue, same thing. States F. I knew how to do it with logarithm, but I thought it will be very slow with a set or priority queue. No, I thought that the issue is different. It was hard to understand statements? I don't know, was it? Maybe I should look critically at the problems. Let's see, what do I think about them? First, of course, well, easy, boring. Second, I don't know, normal constructive problem. Third, the statement wasn't very easy to understand. I didn't even know that those are dots. The drawing helped a lot. So statement was more complicated than the problem was difficult. But I always appreciate ideas from real life. So yeah, fine. D. I'm ashamed that I didn't solve it. Ashamed slash embarrassed, maybe that's a better word. It's a combination of two well-known tricks, but because even though it's well-known, I didn't get one part, so maybe I shouldn't criticize. It was too hard for this slot. Cryptolites. For me, very easy. For some people, much harder, so I guess fine. And F. It seemed doable from the very beginning. I knew what to do. I spent less time thinking about F than about D. So it's not real life. The idea for the statement is from real life. You know, wait, yeah, see, exactly. G. I don't know the solution for G. I've read the problem because when I was stuck on D, among the last three problems, F, G, H, G was solved first by tourist, so I've read it and I thought about it for a few minutes. I even made a drawing. I can show you the drawing. My drawings for second last problem, and in general those are my notes for DP problem. Yes, very nice handwriting. I didn't read H, but I can believe it's very hard. So yeah, that's it, and the last thing I want today is to know my new rating, not just from predictor. Because predictor for sure can be wrong by one or so. What's this? Problem D was SOS. There is compare button. Previous submission. I want to see what my friend messed up. We need to not only, oh, I see. He chose the biggest mask instead of choosing the one with most bits on. Why did it pass pre-tests? That's crazy. Well, there is this thing outside the for loop, so maybe that's then understandable. Oh, I see. So only for big tests it becomes an issue. That's unlucky. Is there non-randomized solution for D? I don't know. Look at editorial. If there is something like that, the editorial will show that. I want to now finish the stream, but also I want to see the new rating. I don't have anything to do now though, so maybe finishing the stream is the better option. Right. Wait, does this not work? No, it works. So see you Monday, Tuesday. Tuesday evening I will make some Google Code Jam preparation stream where I will solve past problems. Maybe I will solve more interactive problems, I don't know. So follow on Twitch, subscribe to YouTube, all that stuff. And then no streams for a week because I won't be in Warsaw. So that's the announcements for today. I want to thank you all for watching. Hope you did well in a contest. Oh, I know where I can see why people complain so much. Here. Statements were that bad? ABC were rubbish? Yeah, I don't know. AB are always easy. Misread E that he continues turning lights on until K are on. Somebody in the chat asked this today. If ain't I couldn't solve it, it means it's very difficult or unsolvable. Yeah, random still sucks in Windows, so in Codeforces, because Codeforces runs on Windows. There was something about changing the statement. Wait, what? We need to say what's the smallest lexicographically? What was the change here? Okay. I didn't see that in the statement, so I'm just lucky that my solution worked. This is not immoral, this is pretty standard stuff in Codeforces. It's not your fault the round is shit. So maybe the rounds will be unrated. But most likely just Mike will say for those affected something. He will make unrated few people and then I can lose 1 point of rating. A lot of people misunderstood it, so apparently it was badly written. Tried all possible subsets. Whoa. Yeah, there are 30 sensible currencies. I noticed that too. But I didn't know that 2 at 30 is possible. Nice. Or maybe the tests are weak. So here's the challenge, if somebody wants to try that. you can first check that with some asserts, but this is a solution that maybe is hackable. First I would do this. Somewhere he finds relevant bits. You can first submit the same code with assert that the number of those bits is at most, let's say, 27 or so, or at most 29. Maybe tests aren't that strong and this value doesn't hit 30. Because if you count frequencies of every bit, and you look only at bits where frequency is at least n over 2, you will get 30 interesting bits, not 60. I noticed that too, but 30 is still too big. Maybe this is not 30, maybe this is 26 in tests, and then it's indeed fast enough. Somebody tried the same thing but got time limit exceeded. Alright. C is the worst problem I have ever seen. I understood it thanks to the drawing. Okay, one last look at my rating. Maybe it's updated now. Nope. So still hoping for 3000, even after some making the round unrated for a few people. Thanks you all for watching again, and see you in 2 days, on Tuesday. I will make Google Code Jam stream, then there will be actually Google Code Jam in 1 week. Alright, bye.